this mic. Can you hear me like this better? Okay. Yeah, so the overall idea here is I basically wrote a little extension to the Haskell type checker that allows it to use an SMT solver. So now this is implemented in GHC, but the ideas, I think, should apply to any other functional language as well. So without further ado, why am I doing that? Well, we all probably agree that Haskell's type system is pretty great. It catches a lot of simple mistakes, and it makes it very easy to, refactor large code bases. You can encode certain invariants. Don't get too ambitious. But yeah, you can encode invariants, and the compiler helps you and ensures that they're followed everywhere. However, for a long time, I've been wanting to kind of manipulate data structures such as bit vectors and arrays and so on. And in pretty much all languages, you can say, yes, this is an array of 10 elements or something. You can say that in C, but then the type system quickly gives up. It oftentimes doesn't follow on. You quickly have to start swapping things to void pointers in C. And in Haskell, we can kind of do it, but not really. And so I've been kind of playing around with, teaching GHC a little bit of arithmetic so you can type check operations such as appending to bit vectors or multiplying matrices together and have it keep track of the sizes of everything. And so in this talk, I'm going to present one technique for solving numeric constraints, which is not mutually exclusive to other techniques. So in fact, I'm a very big proponent of using this together with other stuff. So to give you an example, you have probably seen that in many dependently typed talks, we want to have maybe vectors of length n, and I didn't give their definition here, but the type vec NA is a vector with n elements that are of type A, and then we would like to write the reverse function or something like that without having to do too many proofs. So this is pretty much exactly the way you'd probably write reverse in Haskell. You start with an accumulating parameter called new, and then if you say new, you return the accumulating parameter. Otherwise, you get the first element of the list, and you add it to the accumulating parameter. So completely standard stuff. And hopefully, on this slide, you see, I wanted to show that, you can have type inference. For example, I didn't have to write the type for vec reverse itself. But in some places, you do have to write type signatures. So this is const and new there. This vec type is a GADT. And just by the virtue of how GADTs work in Haskell, how they're type checked, you have to write the type signature so that the type inference algorithm is not ambiguous, essentially. And so if you use the plugin that I developed for this talk, this actually type checks now. And so that is very pleasant. Okay. So for the rest of the talk, I would really not tell you so much about how the actual algorithm works, but kind of what are the sorts of things that GHC does internally, and what are the basically generic things a type checker needs to do, except that I'll be careful to phrase them just in terms of logic. So this was my goal, because then it makes it quite easy to integrate it with SMT Solver, but I think it provides a nice way of thinking of the actual type checking algorithm. So the main thing the type checker does is something like that. So it basically collects these implication constraints. So if you consider some kind of definition in Haskell, we have some function, and it has a type signature that has some kind of context. So here I've written C of A. Think of that as generally some kind of qualifiers on the type. And then you have some type T. So maybe that is some kind of function or some kind of value. It doesn't really matter. And the function has some definition def. Now, how do we type check such a thing? So if we know that def has type S under assumptions D of A, okay, then, well, S and T are clearly not the same thing, at least syntactically, so GHC needs to do some proving. So what is the thing we need to prove? We need to prove that for any A, the declared constraint C of A imply the assumed constraints D of A, and then the type of the definition matches the declared type. So this twiddle thing is GHC's way of writing equality between types. When I first presented it, people asked me about what that means, so that's what that is. And in this talk, I might be switching every now and then between normal equality and this twiddle, and it means the same thing. Okay? So hopefully that makes sense. So given such an implication, GHC needs to solve it. But really, that's kind of not all that it needs to do. It has more work. So one of the proof techniques that it kind of does is, so this kind of reasoning principle is a valid one. It says that basically, if you have some assumptions and you can derive some more facts from these assumptions, well, it is safe to assume these assumptions also, right? So this is a kind of forward reasoning if you look at it from the theorem proving community. And so in particular, if we have a goal such that says for all C, we need to prove D, and we know that C implies E, then we can throw in E as another assumption. Okay? And so why might you do that? You might do that because in this way you can get some modularity between various reasoning bits in the compiler. So for example, the bit in the compiler that knows about numbers can infer some fact about number that perhaps can be used by the class system then to kind of pick the correct instance for something. A special case of this previous reasoning principle is quite important. So if you're trying to prove C of A implies D of A, and somehow you manage to prove that from the assumptions you can deduce false, in other words, your assumptions are inconsistent, then you've essentially detected some unreachable code. So a function equation that is useless, essentially, and can never be called. So at this point, you could choose to trivially solve all the goals from a logical perspective, but in a practical type checker, what you usually want to say is report some kind of nice error to let the programmer know that, you know, they've written some code that could never be executed. So this is fairly important. So this was all working with the assumptions. The other bit, and this is probably the trickiest and most important, is the observation that you can use the constraints that you're trying to prove to do type inference. And in fact, oftentimes you have to do that in order to solve the constraints. So here we say, if we have a goal, it's the same goal in all the examples, I should say, that C implies D, and somehow we know that C and D together imply some kind of equation, alpha equals tau. Okay, here alpha is supposed to be a unification variable or one of those type inference variables, existential variables, essentially, that the compiler is trying to figure out. Then without loss of generality, we only need to really solve the constraint for when alpha is actually equal to tau. Now, why is that? This is basically what this fact says, that if C and D are ever to hold together, then alpha must be tau. So then we are not going to lose any generality if we only solve the goal for when alpha is equal to tau. Notice that in general, for this unification variable, it is always sound to pick whatever type you want for them. So this is something I hadn't realized for a long time, in the sense that you would never type check an incorrect program. However, if you're not careful when you pick the types for unification variables any odd way, you're of course going to reject a lot of valid programs. But if you're not worried about that, it is always safe in a way to pick a type. So essentially, this middle equation there tells us that by picking the type, we are not losing any generality, and we are essentially not rejecting any valid programs. And then the special case of that for false, it is kind of analogous to the first case, is if we notice that the assumption and the conclusion together are inconsistent, well, then we know that this goal would never work, and we want to report an error. And notice that this is, again, slightly different than simply not solving the constraint, in that this tells us that, look, you've actually written a contradiction. There's most definitely a type error here. While the other one, when we can't solve the constraint, it's possible that maybe you didn't specify the types enough, and so the compiler can't solve the constraint because something is ambiguous or it doesn't have enough information to solve the constraint. In this case, we definitely know that we found the type error. Okay, so these are basically the main things that the compiler really needs to know. So here is a summary of that. So the high-level tasks, there's 4 of them. It needs to be able to solve goals, of course. It needs to detect unsatisfiable assumptions, in other words, unreachable code. it needs to detect unsolvable goals. So these are the errors I was just talking about. And very importantly, it needs to compute derived facts, which are these facts for type inference. So basically, the solving of the constraints and type inference kind of go together. They're not completely separate. Sometimes you need to unify and instantiate some variables, which enables you to solve more constraints. And the fifth thing I talked about is really this computing additional assumption is the ability to derive new facts from the given facts. Okay, and so for each of those now I'm going to tell you basically, so the idea is, well, can we use an SMT solver to basically do these tasks? And the answer is yes. So why might we use an SMT solver? An SMT solver basically is a collection of decision procedures that work together well. And so you can think of it as a kind of simple sort of tier improver. And typically the kinds of theories that SMT solvers tend to know about are linear arithmetic on integers, or actually non-integers too, rational numbers and so on. They're very good at that. They're good at propositional logic. I mean, essentially they have a SAT solver built into them, so any kind of Boolean formula with uninterpreted functions, they can deal with that very well. And there's all kinds of interesting theories that they support, the theory of arrays, algebraic data types, sets, and so on. So what I was thinking is, hey, if we can hook in an SMT solver in the type system, all of a sudden we can play with all these interesting types. Now, I only really have useful examples for the linear arithmetic and integers. This is what I was really interested in when I started this work. But maybe there are uses for the other ones too. I don't know. And okay, so let's revisit the exact same thing I showed you. So how do we? So here the goal is the sum one, and how do we prove goals? So the SMT solver needs to know that. This is completely standard use of the SMT solver. The way to think of an SMT solver is it has a state that contains a whole bunch of constraints, a conjunction of them. And you can at any point ask it, hey, all these constraints that you have in your state, are they consistent? And the solver would say, no, they're not consistent. You can't, in other words, you can't find assignments for the free variables to make them all true. Or it would say, yes, they are consistent, and here is an example. So very simple. This is all that it says, either yes with an example or no, and sometimes they produce a proof when they say no. But basically, to prove something, we just assert the assumptions, we assert the negation of our goal, and then we check. And if we get unsat, that means that it is impossible to have both the assumption and the negation of the conclusions, so therefore the conclusions must hold. So it's a kind of a proof by contradiction that you do. In other words, you ask the SMT solver, hey, can you find a counterexample where the assumptions and the conclusions will contradict each other? And if the solver says it is impossible for them to contradict each other, then you say, okay, I've proved the goal. So this is the basic mode for just when you just need to prove things. But as I said, there's other things the GHC needs to do. So checking for consistent assumptions, that's easy. That's exactly what the solver is for. So you assert the assumptions and you say check. And then if the solver says unsat, then you know that you have found assumptions that they contradict with each other, and then you report the appropriate error. If it says sat, then you're good. Then you know that there's at least one example where your assumptions could work together. And you can actually use this model, as I'll very briefly talk at the end of the talk. Impossible goals. This is also quite trivial. So you do the same sort of thing. You assert the assumptions, you assert the goal, and you say, well, can you find one example where both the assumptions and the conclusions hold together? If the solver says unsat, then you know that it is impossible to solve the goals, right? So then you report an error. Otherwise, you have an example that says that you can instantiate this function at least in one way, basically. Okay, so these were the easy cases. The tricky case is how do you do this improvement business, in other words, the type inference business, okay? And so this is very important because the whole thing really does not work well if you don't do that. But what's tricky about it is that there's all kinds of facts you might want to infer. How do you know which ones to infer? And so this is where basically I've used this kind of general idea of using the model, which I think works to some extent, but it is not the full story. So in other words, the algorithm that I have is incomplete. So it won't infer everything that it could possibly infer. It just infers some things, and that's where more work is needed, I think. But generally, notice that in the previous checks, we always did this: assert the assumptions, assert the conclusion, and check for an example. And so now when we check for an example, the SMT solver, when it said SAT, it actually gave us a model of this assertion. So the idea here is, well, we don't want to throw this model away. Maybe we can use it and try to generalize from it. So, for example, essentially the idea is that we use this model as a source of a hypothesis. So, for example, if the model said this variable, alpha, must be 5, so now you would like to know, is this just an artifact of this specific example, or must this variable alpha be 5 always when these constraints hold? Okay? And you can actually ask the solver to prove that too. So I'm going to illustrate that. It's a fairly simple algorithm, but I'll illustrate it just by example and kind of finish there. Okay, so spend a little bit of time. So to keep things simple, we are not going to have any assumptions. We just have goals. So we have two goals here. So we want to say, suppose the compiler inferred constraints that 5 times alpha must be more than 7 and 10 times alpha must be less than or equal to 20. And I did all that by hand. I didn't actually type it into the SMT solver, so hopefully there's no bug in it. Okay, so now if you try to prove that in the solver is going to say, well, you remember when you prove things, we are going to negate this conjunction. And so the solver is going to say, the negation is actually satisfiable, because we can certainly find examples where the negation of that holds by just picking various values for alpha. For example, if we picked alpha equals 0, then we get 5 times alpha is 0, which is not less than or equal to 7, so the negation holds. Right, so the solver can't prove that goal as it is. Okay? So next it's going to say, well, let's see if these constraints are possible to solve at all, right? So it's going to assert them, and it's going to say, okay, are they satisfiable? And the solver is going to say, yes, indeed, they are satisfiable. Oh, this x should be alpha. I apologize for that. When alpha is 2. So it found an example. So when alpha is 2, we have 5 times 2 is 10. This is more than 7. And 10 times 2 is 20, which is less than or equal to 20. So indeed, we have an example. Okay, and so this is the idea now with the improvement, where we say, okay, well, in this concrete example, alpha must be 2, but must it always be 2 under this assumption? So what we do is we try to assert the negation. So in other words, prove, do these things imply that alpha is equal to 2? So we assert them again, and we also assert, this x again should be alpha, I apologize. Assert that this is not equal to 2, and at this point the solver says unsat. In other words, we know that this fact that alpha is 2 is not just due to some random choice, but in fact these constraints force the choice of alpha to be 2. Okay, so once we've done that, then we know that we can basically instantiate alpha to be 2 without losing any generality. Okay, and then the constraints we really have to solve are 5 times 2 more than 7 and 10 times 2 less than or equal to 20, which are now trivial to solve with the solver. So this is the general idea. So this is improvement with a constant. The other improvements I check for are 2 variables equal. And then I have some other kind of more complicated and ad hoc ones to find linear relations between variables. Yeah, so in general, what kind of additional generalizations from the model might you use is, it's kind of a little bit of a black art, I think, and I think that more research is needed. What is neat about this generalizing with variables and constants is that it really is not specific to numbers in any way. So it will work for any theory whatsoever, Booleans or arrays or what. So it at least gives us a first kind of stepping stone to start with. And so I see my time has just run out, so I will give you the conclusion. So there is an implementation of that on my GitHub page. I really should put it on Hackage. I apologize, I have not packaged it up properly. If you want to play with it, it's implemented as a GHC plugin, which is some work that Adam and I have been working on GHC. Yeah, and I think that I'll just end there. Okay, and I'll be happy to answer any questions.
So I apologize if I missed this and you already presented this. Could you give an example of what type of types I'm able to now infer and take advantage of this with?
So the question is, what can we infer using that?
Yeah, for a practical example of I'm writing some code.
Well, that very first example I gave, you need that to get it to work, or, well, something like that. So this example gives rise of all kinds of constraints where you need to know about numbers to solve them. So, for example, here from the type of new, it's going to say, well, it needs to know something like 0 plus x equals x. And for the other one, it needs to know, I think, associativity or something. Yeah.
Do you generate any kind of evidence, any kind of proof terms?
No. In the current implementation, which is very much kind of a prototype, I should say also, in GHC it just puts fake evidence. It says, just trust me, the SMT solver said so. However, some SMT solvers do produce proof terms when they say unsat. So potentially we could look into kind of translating those into the GHC language, but I haven't done that.
Thank you.
I think I must have missed it. What in that example where you were showing that x or alpha must be equal to 2, remind me again, what happens if you find that 2 works, but it's not the unique one?
Then you just don't do any improvement. So then you just keep going, basically. Okay. So say, I don't know. So as I said, I actually have a few other things it will try. So it will try, okay, well, maybe I need to prove x equals to y if in this particular example x and y happen to have the same value. So try to generalize that, maybe they're both, must be equal.
I see, so the improvement is always optional.
Yeah, so sense, right? It is always optional to infer these things, but if you don't do it, then you won't be able to type check the program.
So I guess I would appreciate some more details on examples on improvement. So I'm hoping that this example requires improvement. Can you say a bit about what was improved? And you on the last slide, you talked about how it's not complete for type inference. Maybe that also something that requires improvement. I guess some concrete examples, I appreciate that.
So is the question is about the completeness? Sorry,
well, okay, how does
mics a little bit?
I'm sorry. Can you hear me now?
Yeah.
Okay. In this example, I'm hoping it requires improvement. Can you just say a bit about what the improvement that's done in this example is? What will happen if you don't have any improvement for this example? Other example where it shows that type inference is not complete?
Well, it is generally kind of hard to see that. But so maybe I can show you an example afterwards. So basically, GHC, when it infers this, it puts unification variables all over the place. So if you don't do these things, it just ends up with constraints kind of like the ones I showed you at the beginning, something like, it has a variable and then it can't solve it. So where you need the improvement is, so for example, if it will have something like x plus 0 equal to y, but maybe somewhere else it needs to know that x and y must be equal. So without the improvement, it's going to say, well, I have no reason to believe that x and y are equal.
So I see that it makes things prettier, but I don't yet see that it makes things incomplete, because if GHC wants x to be equal to y, I think nowadays it just says x tilde y, right? So it seems that it will still go through, you just get some ugly big type at the end as opposed to the pretty type.
Oh, right. When you really need to do that business is when there's a type signature or something, and so then you're not allowed to just kind of add more constraints to it. So yeah. Sometimes it will work if you don't have a type signature, because then it will just, delay constraints and can't solve, essentially. We can chat some more offline if you'd like.
How performant is doing all these round trips to the SMT solver?
Well, not super performant, but so first the way I showed it here is not exactly how it works. So a lot of the solvers are incremental. So if you notice, there was a lot of duplication between the assumptions I was doing, so you don't actually assume all the things all the time. So instead it has a kind of a stack-based discipline where when you've asserted a thing, you can kind of mark the stack and then you assert some more things and then you unassert them. Okay, so at least that part kind of is not bad. I've only tried it on really small examples and it works fine. Now in general, the good thing about that is that it is it's modular. As long as your function is not huge and it has a million constraints, the kind of questions you ask of the SMT solver are very simple here. So, yeah. But also the implementation communicates over a pipe via text, so that's not super efficient, really.
Could you just say a little bit about how this compares with Liquid Haskell?
With Liquid Haskell. Yeah, so they do kind of slightly different things. In that Liquid Haskell, in a way, is a lot more expressive. It allows you to basically kind of have all kinds of properties about, the type system, like the subtypes and so on, which you couldn't do with this. On the other hand, this is kind of a lot more integrated into Haskell, right? So all these number types and so on, they're just another type. So now all of a sudden the type checker knows about that. So I really kind of think of them as complementary techniques. I mean, I want this to kind of keep track of the sizes of my bit vectors. I want Liquid Haskell, to prove my vector library correct, So I mean, I think they both use SMT technology, but I think that they're kind of different for what they're trying to do.